Since the earliest ancient astronomers studying the night sky in regions like Palestine, modern-day Israel, around the 3rd millennium BC, humanity has looked up at the stars and wondered about our place in the vast cosmos. For thousands of years, our ancestors charted the movements of the planets and the constellations, trying to make sense of the celestial dance playing out above their heads. This deep-seated desire to understand the universe has driven centuries of scientific inquiry, leading us from rudimentary stone observatories to the sophisticated space probes of the modern era. Fast forward to 1977 AD, a pivotal moment in human history when we finally possessed the technology to not just look at the outer planets of our solar system, but to actually send emissaries to visit them. This was the birth of the Voyager program, an ambitious undertaking that would fundamentally change our understanding of the neighborhood in which our small blue planet resides. Imagine floating in absolute freezing darkness, moving at a staggering speed of roughly 38,000 miles per hour. You are completely alone, more than 15 billion miles away from home. The sun, which gives warmth and life to everything you have ever known, is nothing more than a slightly brighter, unblinking star in an infinite sea of black. This is the current, mind-bending reality of Voyager 1, the farthest human-made object in existence. It has been traveling through the cosmos for nearly half a century, leaving the protective bubble of our solar system and venturing into the uncharted, mysterious territory of interstellar space. For decades, it has been a reliable, steady presence, a mechanical explorer dutifully sending back a continuous stream of invaluable scientific data and engineering updates. But recently, this intrepid explorer started exhibiting strange, deeply concerning behavior. The stream of coherent information it had been sending back to Earth suddenly turned into an unintelligible, repeating sequence of ones and zeros. Voyager 1 simply stopped making sense. It was as if a trusted friend, communicating from the deepest void, had suddenly begun speaking in a fractured language no one could understand. For months, scientists and engineers on Earth worked tirelessly, grappling with decades-old technology and agonizingly long communication delays to figure out what went wrong and, more importantly, how to fix it before the spacecraft was lost forever. This is the incredible story of how an aging spacecraft lost its mind in the deepest depths of space, and the unprecedented ingenuity and dedication required to bring it back to life. To truly appreciate the magnitude of this crisis and the brilliance of its ultimate resolution, we must first travel back in time to the origins of this extraordinary mission. The year was 1977 AD. It was an era when computing power was in its absolute infancy. The modern smartphones we carry in our pockets today have millions of times more memory and processing capability than the massive computers that were painstakingly installed on the Voyager spacecraft. The onboard computers had to be robust, reliable, and capable of operating entirely independently for long periods, but by any modern standard, they were incredibly rudimentary and severely limited. The primary mission of Voyager 1, along with its twin sister ship Voyager 2, was to take advantage of a rare planetary alignment that occurs only once every 175 years. This unique alignment allowed the spacecraft to use the gravity of each giant planet to essentially sling them onto the next, a clever orbital mechanics technique known as a gravity assist. This grand tour trajectory would allow the probes to visit Jupiter, Saturn, Uranus, and Neptune in a fraction of the time, and with a fraction of the fuel it would normally take to reach them individually. Voyager 1 was launched on September 5, 1977 AD, slightly after Voyager 2. It was placed on a faster, more direct trajectory, reaching the massive, turbulent gas giant Jupiter in 1979 AD and the beautiful ringed planet Saturn in 1980 AD. The images and data it sent back during these flybys completely revolutionized our understanding of these giant planets and their intricate, complex systems of moons and rings. We saw active, erupting volcanoes on Jupiter's moon Io, a world being constantly stretched and squeezed by Jupiter's immense gravity. We peered through the thick, smoggy, orange atmosphere of Saturn's moon Titan, finding a world where it rains liquid methane. The Voyager probes showed us that the outer solar system was not a collection of dead, frozen rocks, but a dynamic, incredibly active region filled with geological wonders that rivaled anything found on Earth. Having successfully completed its primary planetary objectives, Voyager 1's path naturally bent upward, taking it out of the ecliptic plane, the flat disk in which all the planets orbit the Sun. It was now headed towards the very edge of our solar system, beginning its long, lonely interstellar mission. On board this mechanical explorer is a profound, beautifully crafted time capsule, a literal message in a bottle cast out into the cosmic ocean. It is the Golden Record, a 12-inch gold-plated copper disc containing a carefully curated selection of sounds and images designed to portray the vast diversity of life and culture on Earth. It holds greetings spoken in 55 different human languages, natural sounds of ocean surf, rushing wind, and cracking thunder, the haunting songs of birds and whales, and a musical selection ranging from classical symphonies to indigenous folk music from all around the world. It was specifically designed to communicate a story of our world to any extraterrestrial intelligence that might one day, perhaps millions of years from now, encounter it. The record stands as a lasting testament to human hope, our deep-seated desire to connect with the wider universe, and our wish to not be forgotten. The inclusion of this record transformed Voyager 1 from a simple scientific instrument into an ambassador for all of humanity. In August 2012 AD, Voyager 1 achieved a historic, unprecedented milestone. It crossed the heliopause, the invisible boundary where the continuous outward flow of charged particles from our Sun, known as the solar wind, gives way to the interstellar medium, the exotic matter that exists in the vast, empty spaces between star systems. It officially became the first human-made object to enter interstellar space. Since then, it has been providing our very first direct, in situ measurements of this unexplored realm, tasting the environment between the stars. It has continued to function against all odds, a solitary sentinel in the dark, transmitting data back to Earth via its 23-watt radio transmitter. The signal is so incredibly faint by the time it reaches us that it requires the massive, highly sensitive antennas of NASA's Deep Space Network to detect it at all. However, the incredibly harsh environment of deep space and the relentless, unforgiving passage of time take their inevitable toll on even the best engineered machines. On November 14, 2023 AD, the steady, reliable stream of coherent data from Voyager 1 suddenly ceased. Instead of the familiar structured packages of engineering and science telemetry, the Deep Space Network began receiving a repeating, alternating pattern of ones and zeros. It looked as though the spacecraft's computer was stuck in some sort of infinite loop, entirely incapable of processing or transmitting its data correctly. The engineering team at NASA's Jet Propulsion Laboratory in Southern California quickly realized they had a major, potentially mission-ending problem on their hands. The issue was quickly isolated to one of the spacecraft's three primary onboard computers, specifically the Flight Data Subsystem, or FDS. The FDS is a crucial, central component of the spacecraft's architecture. Its job is to collect raw data from the various science instruments and engineering sensors, format that data into organized packages, and hand it over to the telemetry modulation unit, which then beams it back across billions of miles to Earth. If the FDS cannot properly package the data, absolutely nothing intelligible can be sent. The spacecraft was still alive, it was still receiving and executing basic commands from Earth, and the radio transmitter was still functioning perfectly. But the central brain responsible for organizing the information had essentially suffered a catastrophic stroke. Troubleshooting a complex machine built in the 1970s AD is challenging enough when it sits on a clean lab bench directly in front of you. Doing so when the machine is 15 billion miles away is a task that borders on the impossible. The communication delay is staggering and incredibly frustrating. Because light and radio waves travel at a finite speed, it takes 22.5 hours for a signal from Earth to traverse the vast distance and reach Voyager 1. It then takes another 22.5 hours for the spacecraft's response to travel back to Earth. That means every single time the engineers sent a command, they had to wait an agonizing 45 hours to see if it had any effect. A simple, basic back-and-forth conversation took nearly 2 full days. This massive delay meant that the team had to be extremely deliberate, cautious, and thoughtful with every single action they took. There was absolutely no room for rapid trial and error. Furthermore, the engineers working on the problem today were, in almost all cases, not the ones who originally designed and built the spacecraft. The brilliant original designers have long since retired or passed away. The current younger team had to dive deep into the dusty archives, poring over decades-old documentation, hand-drawn schematic diagrams, and internal memos written on typewriters, desperately trying to understand the intricate nuances of a computer architecture that predates the personal computer revolution by decades. They had to teach themselves to think like engineers from 1977 AD, understanding the severe limitations and the highly specific, idiosyncratic logic of the FDS. The first step was to try the most basic troubleshooting technique known to computing, the equivalent of turning it off and on again. They attempted to restart the FDS to its default, baseline state, hoping that a simple reboot would clear whatever transient error had caused the infinite loop. They carefully sent the command, waited 2 long days, and received the exact same alternating pattern of ones and zeros. The reboot had completely failed. The problem was clearly deeper and more permanent. It was not a temporary glitch. Something fundamental was physically broken within the computer's memory or its processing hardware. The team spent months painstakingly formulating a new strategy. They needed to find a way to force the FDS to tell them exactly what was wrong. In early March 2024 AD, they decided to send a carefully crafted poke command. This command was designed to gently prompt the FDS to try executing different sequences in its software, in the hopes that it would somehow bypass the corrupted section and send back a full readout of its internal memory state. The command was a masterpiece of engineering, taking into account the known, ancient architecture of the computer and the extremely limited set of commands it could still process in its damaged state. They transmitted the poke on March 1st. 2 days later, on March 3rd, the giant antennas of the Deep Space Network received a faint signal. At first glance, it looked like the exact same gibberish they had been receiving for months. But one observant engineer on the Deep Space Network team noticed that the repeating pattern was slightly different. It wasn't the exact same sequence. It contained a distinct variation. The team eagerly fed the signal into their decoding software, and to their immense, overwhelming relief, they found that the spacecraft had indeed responded to the poke command. The signal contained a complete, unfiltered readout of the entire FDS memory. This memory dump was the critical key they had been searching for. By carefully comparing this new readout to a known, good copy of the FDS memory from before the anomaly occurred, the engineers could pinpoint exactly what had changed. The detailed analysis took several weeks, requiring meticulous, line-by-line attention to detail. Finally, they identified the specific culprit. A small but critical portion of the memory, approximately 3% of the total, had been severely corrupted. This specific corrupted section contained crucial software code responsible for operating the FDS and packaging the telemetry data. The corruption was ultimately traced to a single piece of hardware, a dynamic random access memory chip. It is completely impossible to know exactly why the chip failed after 46 years in the harsh environment of space. It could have been slowly degraded by decades of exposure to extreme, freezing cold and background cosmic radiation, or it might have simply suffered a random, unlucky strike from a single high-energy particle traveling through interstellar space. Whatever the specific cause, that particular chip was irrevocably dead, and any software code stored on it was permanently inaccessible. If this failure had happened on Earth, a technician would simply open the casing and swap out the bad chip for a new one. But Voyager 1 is forever beyond the reach of any repair mission. The hardware was permanently broken. The only possible way to save the mission was through an incredibly complex software fix. The team had to figure out how to operate the FDS without ever using that specific damaged section of memory again. They had to somehow relocate the corrupted code. This sounds relatively simple in theory, but in practice, it was a monumental, historic challenge. The total FDS memory is incredibly small, and it was already tightly packed with essential instructions. There was absolutely no single empty block of memory large enough to hold all the relocated code together. The engineers had to divide the affected code into much smaller segments and creatively store those individual segments in various tiny, empty spaces scattered randomly throughout the remaining healthy memory. But it wasn't just a matter of blindly cutting and pasting code. The software on Voyager 1 was written in a highly optimized, extremely low-level assembly language, completely specific to that particular archaic computer architecture. Every single line of code was intimately connected to the memory addresses immediately around it. When a section of code was moved, it completely broke the intricate links between it and other parts of the program. The engineers had to meticulously rewrite the code from scratch, carefully adjusting the memory pointers and ensuring that the newly fragmented pieces of software could still find each other and function as a seamless, cohesive whole. Furthermore, any references to the location of that code in completely different parts of the FDS memory had to be manually updated. A single tiny mistake, a single incorrect memory address, could crash the system completely, permanently silencing the spacecraft forever. The painstaking coding process took weeks of intense focus. They tested and retested their complex patch in ground-based simulators, virtual reconstructions of the 1970s AD computer hardware built specifically for this purpose. They had to be absolutely, unconditionally certain it would work before sending it. Finally, they were ready. Because they couldn't risk moving all the affected code at once, they smartly decided to start with the most critical part, the specific code responsible for packaging the spacecraft's basic engineering data. This would finally allow them to see the basic health and status of the spacecraft and confirm that their software fix was actually working as intended. On April 18, 2024 AD, the team transmitted the command to relocate the first section of code to a new location in the FDS memory. They held their collective breath as the invisible signal began its 22.5-hour journey across the vast expanse of the solar system. Then began the agonizing, stressful wait for the response. 45 hours after they transmitted the command, the Deep Space Network antennas picked up a faint, familiar signal. It was instantly processed and routed to the control room at JPL. The data scrolling across the monitors was no longer a meaningless, frustrating pattern of ones and zeros. It was coherent, highly structured engineering data. Voyager 1 was finally talking to them again, and it made perfect sense. For the very first time in 5 long months, the team could clearly see the vital signs of the beloved spacecraft. It was healthy, it was operating normally, and the intricate software patch had worked flawlessly. The immense relief and unbridled joy in the control room were palpable. They had successfully performed unprecedented long-distance brain surgery on a machine billions of miles away, using nothing but radio waves and sheer, brilliant human engineering. But the arduous work wasn't finished yet. Over the next several weeks, the dedicated team carefully relocated and meticulously adjusted the remaining portions of the affected code, piece by piece, checking their work at every step. They slowly and methodically brought the various science instruments back online, restoring the spacecraft's unique ability to measure the cosmic rays, magnetic fields, and strange plasma of interstellar space. By mid-May 2024 AD, 2 of the 4 remaining science instruments were successfully returning highly usable data. By June, all 4 instruments were entirely back in operation. Voyager 1 had miraculously returned to normal science operations. The incredible recovery of Voyager 1 is a lasting testament to the phenomenal resilience of the spacecraft itself and the unparalleled skill, dedication, and ingenuity of the people who continue to operate it. It starkly highlights a unique, growing challenge in deep space exploration. As missions stretch from years into decades, the essential knowledge base required to maintain them becomes historical as well as technical. The engineers working today are actively preserving a legacy, keeping alive a piece of technology that represents a very different, bygone era of human history. The solutions they devise are not just brilliant technical fixes, they are acts of historical interpretation and technological preservation. The spacecraft itself remains a true marvel of engineering. It was deliberately built with multiple redundancies and incredibly robust systems that were explicitly designed to handle the unexpected and the unknown. But even the absolute best engineering cannot defy the fundamental laws of physics forever. Voyager 1 is powered by radioisotope thermoelectric generators, which cleverly convert the heat from the natural steady decay of plutonium-238 into usable electricity. As the plutonium naturally decays over time, the total power output steadily and unstoppably decreases. Every single year, the aging spacecraft has slightly less energy available to operate its essential heaters, its scientific instruments, and its vital radio transmitter. To dramatically conserve this dwindling power, engineers have been systematically, carefully, turning off non-essential systems for years. The iconic cameras were permanently shut down in 1990 AD, shortly after taking the famous pale blue dot photograph, a final, deeply poignant look back at our tiny Earth from the very edge of the solar system. Essential heaters have been turned off one by one, leaving the sensitive instruments to operate in the brutal, unimaginable cold of deep space. At some point in the future, perhaps in the late 2020s AD or early 2030s AD, the available power will inevitably drop below the absolute minimum threshold required to operate any of the science instruments or transmit a signal back to Earth. When that sad day finally comes, Voyager 1 will fall silent forever. It will stop making sense not because of a software glitch or a broken chip, but because it has finally, completely exhausted its lifeblood. But even when the radio goes permanently quiet, Voyager 1's epic journey will continue unabated. It is currently moving fast enough to completely escape the gravitational pull of our sun entirely. It will drift silently through the Milky Way galaxy for billions of years, a silent, enduring ambassador from a small, rocky planet that once dared to reach for the stars. Long after our own civilization has drastically changed beyond recognition, perhaps even long after the Earth itself is consumed by the dying sun, Voyager 1 will still be out there, coasting through the void. It will pass near other distant stars, and perhaps one day in some unimaginably distant future, another civilization will encounter it. They will find the golden record, and they will hear our voices, our music, and the sounds of our vibrant world. Until that day comes, we continue to listen intently. The recent, terrifying crisis and its brilliant, triumphant resolution remind us of the incredibly fragile, deeply precious nature of our connection to this distant emissary. Every single bit of data it manages to send back is a hard-won victory against the vastness, the cold, and the silence of space. The story of Voyager 1 is not just about the groundbreaking science it has gathered, it is about the indomitable human spirit that built it, launched it, and continues to stubbornly sustain it across an incomprehensible cosmic divide. It is a story of fiercely refusing to let go, of fighting tirelessly against the dying of the light, and of finding incredibly ingenious ways to keep the conversation going, even when the machine stops making sense. The brilliant scientists and engineers who saved Voyager 1 did much more than just fix a broken computer. They strongly reaffirmed our deep commitment to exploration and discovery. They unequivocally demonstrated that with enough patience, acquired knowledge, and sheer determination, we can overcome even the most daunting, seemingly impossible obstacles. They kept alive a vital, irreplaceable link to our past and a shining beacon of hope for our future in space. As we look up at the night sky, we cannot see Voyager 1. It is far too small, far too far away, and far too faint. But we know with absolute certainty that it is there, hurtling bravely through the darkness, carrying a small, golden piece of humanity with it. It is our farthest outpost, our deepest, bravest probe into the unknown. And as long as it continues to function, as long as the brilliant engineers on Earth can continue to understand its fading whispers, we will continue to learn from it. We will continue to expand our understanding of the universe and our incredibly small place within it. The journey of Voyager 1 is our journey, and it is far from over. The profound silence that followed the glitch in late 2023 AD was deeply felt. It wasn't just a loss of scientific data. It genuinely felt like losing a connection to a piece of living history that had been speaking to us since before many of the current engineers were even born. The spacecraft had long since become a permanent fixture in the daily lives of those who monitored it, a distant, perfectly reliable presence in an ever-changing, chaotic universe. When it suddenly began speaking in tongues, the immense urgency to fix it was driven by much more than just scientific curiosity. It was a deeply felt, personal responsibility to preserve a legacy. The painstaking process of debugging the FDS required a unique kind of technological archaeology. The operating manuals were not easily searchable digital files, but scanned, yellowing copies of fading, typewritten documents from a different era. The code itself was not written in modern, intuitive, high-level languages like Python or C++, but in raw, unforgiving assembly language, a direct manipulation of the hardware's registers and memory locations. Understanding this required a profound, difficult shift in mindset, a willingness to fully inhabit the engineering logic of a bygone era. The engineers essentially had to mentally simulate the precise behavior of processors that were far less complex than the disposable chips found in modern musical greeting cards, yet tasked with independently navigating the harshest environment known to man. This Herculean effort highlights the incredible, almost prophetic foresight of the original Voyager design team. They explicitly built a machine highly capable of operating autonomously for decades, with systems that could be remotely reconfigured and completely reprogrammed from billions of miles away. They deeply understood that they were launching a probe into the absolute unknown, and they designed it to be as adaptable and flexible as possible. The incredible ability to remotely patch the FDS memory, to move critical code around to completely bypass a physical hardware failure, is a lasting testament to that brilliant, forward-thinking design philosophy. It was precisely this foresight that gave the current team the necessary tools they desperately needed to effect a rescue. The highly successful recovery of the spacecraft is also a monumental triumph of patience. In an age defined by instant communication and rapid prototyping, the Voyager team had to stubbornly operate on a timescale strictly dictated by the immutable speed of light. Every hypothesis, every command, every patch required a mandatory 2-day round trip just to receive a basic acknowledgement. This necessitated a slow, highly methodical approach, where every single step was endlessly debated, thoroughly simulated, and independently verified before being committed to space. It was a high-stakes, nerve-wracking game of long-distance chess, played against the unforgiving environment of the cosmos. As Voyager 1 joyfully resumes its observations, the stream of data it sends back continues to challenge and refine our scientific understanding of the interstellar medium. It measures the density of exotic plasma, the strength and direction of interstellar magnetic fields, and the constant flux of galactic cosmic rays. It reveals a highly dynamic, turbulent environment, profoundly shaped by the complex interactions between our Sun's protective heliosphere and the broader galactic environment. These ongoing measurements are unique and completely irreplaceable, providing essential ground truth for theoretical models of the space between stars. Every single day that the spacecraft survives is another day of unprecedented historic scientific discovery. The compelling story of Voyager 1's near-death experience and its miraculous, hard-won resurrection is a powerful, inspiring reminder of what we can achieve when we dedicate ourselves to long-term, ambitious goals. It is a story that completely transcends the immediate scientific returns, touching on deeper, universal themes of perseverance, ingenuity, and the fundamental human desire to explore the unknown. It teaches us that even the most advanced, robust technology is ultimately sustained by human effort, by the tireless dedication of individuals who are willing to spend their lives caring for a machine they will never, ever see again. In the end, Voyager 1 is so much more than just a collection of old instruments and rudimentary computers. It is a physical extension of ourselves, reaching out boldly into the dark. It faithfully carries our history, our art, and our science. It perfectly represents the absolute best of what we are capable of when we work together towards a common, peaceful purpose. And as it continues its long, silent journey outward, long after the last faint signal has faded, it will remain a lasting golden monument to the time when humanity first stepped out of its planetary cradle and into the wider, infinite galaxy.